Black holes don't make sound, but after a merger the universe produces a signal that can be translated into a chirp and a dying ring. Some researchers claim that after the ringdown, tiny repeats appear, echoes, like a reflection from the edge of the horizon. If real, that would hint the horizon isn't a perfect one-way boundary. If not real, it exposes how easily noise can impersonate meaning. Gravitational wave detectors measure strain. Minute changes in distance along perpendicular arms, far smaller than any everyday scale. A merger creates a rising chirp, a peak, and then a fading tail. That tail is where the final object settles into a stable state. Echo claims focus on that fragile tail because it's the hardest part to interpret. In general relativity, the newborn black hole relaxes through quasi-normal modes, its characteristic resonances. Those modes depend mainly on mass and spin, making ringdown a stringent test of black hole physics. In the standard picture, the horizon absorbs rather than reflects. Echoes would imply that assumption fails in some subtle way. Outside a black hole there is a region where gravity strongly traps waves, often described as a potential barrier near the photon sphere. If the horizon were replaced by something slightly reflective, waves could bounce between that barrier and the near horizon region. Each bounce would leak a weaker, delayed copy of the signal outward. That's the physical intuition behind echo templates. Reflective does not necessarily mean a hard surface like a planet. It could mean an exotic compact object, a near-horizon modification, or boundary conditions different from a classical horizon. Many ideas are speculative and model-dependent. The important point is that echoes are a claim about boundary behavior, not about aliens or hidden machines. The echo region sits exactly where detectors are least forgiving. Low signal-to-noise, non-stationary noise, and subtle analysis choices. A small change in filtering can create or erase weak patterns. That makes the story thrilling, but also statistically treacherous. In this regime, confidence must be earned the hard way. If you test one fixed echo model, significance is straightforward to compute. But if you scan many delays, many damping factors, and many events, you inflate the chance of a lucky match. This is the look elsewhere effect. The search itself manufactures apparent discoveries. A real echo must survive accounting for the full search space. A robust echo would repeat across multiple independent events with consistent scaling. Larger black holes should produce longer delays. The pattern should appear in independent detectors in a compatible way, not just in one instrument's quirks. It should also be found in blind analyses where parameters aren't tuned after seeing results. In short, repeatable, cross-checked, and resistant to pipeline choice. Modern detections often involve multiple observatories and careful consistency tests. If an echo appears only in one detector stream, suspicion rises. If it appears with consistent timing and coherent behavior across sites, credibility improves. Echo claims live or die by these sanity checks. In electromagnetic astronomy, echo can mean reverberation. Light emitted near the black hole reflects or reprocesses in surrounding material and arrives delayed. This is a real, widely used method, but it does not imply horizon reflectivity. Same word, different physics, mixing them creates confusion. In some systems, a hot corona emits X-rays that illuminate the inner accretion disk. The disk responds with delayed spectral features because light takes time to travel. Measuring those lags maps distances in the inner region. It's one of the most precise timing tools near black holes, but it still probes outside the horizon. EHT images show a bright ring and a dark shadow, shaped by lensing and plasma emission. This is not a photo of a reflective surface, it's a view of material outside the horizon. The ring's brightness comes from orbital motion and relativistic beaming. Echo claims require timing and waveform evidence, not just an image. Interferometers are ultra-sensitive instruments, so they register environmental and instrumental transients. Some glitches can resemble damped oscillations or repeating patterns. Without careful vetoes, these artifacts can masquerade as post-merger structure. Any echo claim must prove it is not a glitch story. A standard honesty check is to inject simulated echo signals into real noise and see if pipelines recover them reliably. Another is to estimate false alarm rates using time shifts and background methods. This is where the argument becomes concrete, not looks similar, but beats the null hypothesis. Echo debates are decided in these tests. A confirmed echo would constrain near-horizon reflectivity and the microphysics of compact objects. It could indicate physics beyond classical general relativity or an object that mimics a black hole closely. But interpretation would still require model discipline. Evidence opens doors, but it doesn't tell you which room you're in. Failure to confirm echoes would still be a major lesson in scientific humility. It would show how pattern-hungry analysis can overfit weak tales. It would also improve detector characterization and post-merger modeling. In high-precision astronomy, no can be as informative as yes. Right now, echoes remain controversial, reported as hints in some analyses and weakened under stricter treatments in others. That is not a contradiction, it is a sign the question is hard. The honest stance is tension, not certainty. We are testing the boundary between physics and statistics. We definitely hear black holes ring. Echoes are the knife-edge question. A real near-horizon reflection, or a mirage built from noise and search freedom. If they exist, they hint at new boundary conditions near horizons. If they don't, they remind us that the universe is subtle and our tools must be stricter than our imagination.